computer. Okay, sorry about that. We are back. Let's go to share screen. Share screen. Okay, you can see me, you can hear me. We're recording. Not sure what happened. We're gonna have to continue. So regarding the video, go check the Wednesday video. So now this one's gonna be halfway through and then we're gonna resume. So let me know, where did I cut off for y'all? Did I cut off on this slide? Like error estimation? I'm gonna have to resume from here. Okay, I'm gonna resume from here. We have error estimation, and then we have these definitions, okay? All right, sorry everyone, let's continue. So again, we're recording now. So yeah, if you want the recording, then you're gonna have to go to the Wednesday video. So to make sure we're on the same page, we have any questions about this slide for the error estimation? All right. Yeah, so again, keep these in mind because we're gonna need these for checking the tolerance of the solution. All right. All right, so our first method is the bisection method. So how many of you learned this already? Bisection? Okay, all right, perfect, perfect. So the bisection method is similar to what we already covered when I was showing this on MATLAB previously, right? So the first step is to choose an interval between A and B such that f of A times f of B is less than 0. So who can tell me why this equation is true? What's the significance of this equation? What are we doing with that? So we look graphically, right? F of A, say it's positive. F of B is negative. Yes, very good, very good. So there's a root between the 2 points. And so if we have something multiplied and it's less than 0, that means it's negative, right? So in this case, f of A is positive, f of B is negative. So then there's a root between the system. So that's our first step to check whether or not we can actually proceed. The second step is to estimate the numerical solution at the ith iteration using the mean. So now we're just going to take the midpoint between A and B, and that's our initial guess. So with this estimation, now we can determine whether or not we're close to the true value and how do we proceed from there. So this is the tricky part for me. If f of A times f of x and SI is less than 0, right, then the solution is between A and x and SI. So we're looking, in this case, A and x and SI, right? And if it's greater than 0, the solution is between x and SI and B, right? So we're just checking whether or not it's positive or negative, and then we can iterate through that, okay? Noon's method. Noon's method is a much more robust algorithm. The only trick is we need to be able to determine the derivative. So the equation for the same, for the next iteration, so remember xi plus 1 is the next iteration, and it's equal to the previous iteration, that x value, minus the function at that point divided by the derivative at that point. So again, what is the derivative? So this black, right, this black function is our function, and then the derivative is the slope at that point. It's going to give us the slope at that point. Okay, so as long as we have the function and the derivative, then we can use this method to get it, to get the solution faster. So we're starting at x1, calculating the derivative, seeing where it crosses, go back to the function, calculate the derivative, seeing where it crosses, go back to the function, and we iterate that. So in theory, can Newton's method give us the true answer of the equation? If it approaches, 10,000 iterations, will you be 100% fully accurate? No. So with these numerical methods, we're getting approximations. We're getting very, very, very close to the answer, but technically not quite the answer. Okay, so this is the algorithm for Newton's method. All right, and that's going to be your assignment. I think Newton's method is probably the most important one out of all of them. When I was reviewing for this class, I learned a lot about the way that Newton's method is used in modern research. So, you know, Newton already passed several years ago, yet we're still using the same method for modern research in computer science and graphics and lots of things. Cool. So the one that I want to really cover is regular falsi. And the reason I chose this one is because the book didn't cover this. So this one is going to be used to basically follow a similar approximation. Okay. So we have the function, and then we're calculating the function. We're calculating the secant line. All right. So I think what I will do is I'm going to stop share. Then I'm going to close this one. And then I'm going to start that one. And then hopefully that's that. So I'm wondering how to spotlight for everyone later. All right, perfect. So I'm going to move this. Okay. And then I'm going to have this one frozen. Okay. System. All right, perfect. So hopefully we can see that. All right. Okay, so we lost some time, so we have to go quick. So basically, these two. All right, okay. So there's our function. So let's draw our function. Okay. All right. So there's our function. Let's plot the function. It looks like this. Okay, so this is our function of x. Okay, and then we want to solve this point. The goal: solve this x. Solve for root at that point. Okay. So the first step is we need to select 2 points, right? So I'm going to select this A as my initial estimate, okay? And then I'll select this B as my x naught left, and then x naught right, okay? So these are my 2 points, and then I know that the solution is in between these 2 points, right? So with dissection method, we can take the in-between point, the mean, right? And then that's going to give us our initial estimate. But this is slightly different. What we need to do is take the secant line between those 2 points. So I'm going to take this value, and then I'm going to take this value, and then draw the secant line between those 2 points. So now do you see this is my first estimate. This is my first estimate. So is this correct? Not quite. We still have this delta x that we want to get closer to, right? So how do we limit that? So we have these 2 functions. And so this is, what kind of function is this green line? It's a secant line, it's a line. So what's the equation of the line? Yeah. Right? So what we do is we have that derivation. So you don't really need to know the derivations for this class, but if you go through them, they'll help you. And in this case, it's nice because it's only algebra. So I'll make sure this is correct. Okay, so how do we get the m? What is m? Slope. M is the slope, right? So we have, right, B minus A. So that's the slope. We can plug it into here. And then using the slope, we can calculate B. So what is B? Good. Y-intercept. So B, you do some math. So for your homework, for fun, this is for fun now. Fun, do the math, and then you're going to get something like this. F of A minus the slope. Right? So that's that B term, okay? And then what we do now is we plug these two back into here, okay? And then if you do some more math, you're gonna get that function. So what is this equation now? F of x equals f of b minus f of a. B minus A plus f of A. Okay. So what is this? Yes. Very good. And then you do some factorization. You're gonna get the y-intercept. All right. So any questions about that function? So that's that function. And notice theirs is slightly different. So they have x minus b plus f of b. But mathematically, it should be the same because a and b are arbitrary. All right. So now we have the equation of that line. And then that's going to be our first guess. And so our next guess is going to be, again, doing some more math. And we have that equation. Plug stuff around. Set it equal to 0, and then more math. Math, right? And then we have the final equation. What do they write? X and S. X and S equals B minus f of B divided by f of B minus f of A and B minus A. Okay. So these two are your main equations. Okay. So now what we're doing is we're having this solution. We're going back to here. And that's our f of x. We calculate a new secant line. It's going to cross right here, go down, our new f of x, new secant line, and then get closer and closer and closer until we kind of just give up. In your homework, I think you only have to do it like 5 or 6 times and it should work. All right. That's pretty much everything for the regular false line method. So again, the algorithms are they're very similar to each other. So you have some guess and you just get closer and closer and you check that estimation. So how many iterations do we need? So about 6 iterations for today should work. Okay, any questions? Yeah, so a little bit of math, and then we're going to be doing it on MATLAB. So seems like we're kind of okay on time. So let me stop this, go back to this. Okay.
And then back here.
All right. Yeah. So any questions about the methods? So again, we covered the 3 methods. And if I didn't do the other ones, then I want you to go in the book and then read them yourselves. So before we get started, I need to give you guys some tips for the assignment. So number 1, for today's example, you don't need to do for loops, but if you want to use for loops, I need to tell you how to stop the for loop. So you want to do Control-C and Command-C for Mac. Otherwise, it's going to iterate through all those for loops, and then your computer will be mad at you. Okay. So some tips. So for today, again, I want you to write a numerical method. You can do it on MATLAB manually. So I'll explain what that means a little bit better later. But I want you to do everything on MATLAB. So if you do it by hand, make sure you transcribe it onto MATLAB. And then if you want, try to do your own for loops. And so I get this question, like, how do you know whether to do this vector or declare this other vector? So it's about computer languages, right? Computer languages are quite like real languages, in that if you ask someone, how do you know to use this sentence or this word, right? You just kind of get used to it. You just learn how to speak naturally until you're fluent with the language. Someone also asked me, why reinvent the wheel if there's already MATLAB built-in functions to do this automatically, right? Well, all of the methods, this entire class, we're just learning how to reinvent the wheel. And so by all means, if you want to make your own numerical method, then go for it. In fact, if I get an email a couple of years from now saying, hey, Andrew, I published a paper, I made my own method, believe me, I'll be so ecstatic to read that email. So, for this class, we're learning how to reinvent the wheel, but the purpose is to take this further for your other projects. Yeah, and then develop your own algorithm. And seriously, I really encourage you to use MATLAB for your other classes. That's how you can stay fresh. Whether or not it's required, it's super helpful because you're gonna have projects and it's gonna be way easier to use MATLAB than most other languages. In my opinion, that's up to you. And remember that there's an infinite number of ways of solving the same problem. So if you think that my way doesn't work for you, then go ahead and change it. And then last but not least, this is just me nerding out because, this video came out this week, and I think that timing is pretty incredible. And it shows you Newton's method graphically, visually. And then I was so surprised to see how that transforms into modern mathematics and technology. Very beautiful, very geometric. So go ahead and check that out. This is by 3 Blue 1 Brown, came out this week. Really incredible timing. Yeah, so I'm gonna help you get started on the assignment. So we have a MATLAB grader, right? Newton-Raphson, yes. Okay, so we have this function, Newton-Raphson, and so we want to calculate its root. So let's go to the method. So the first thing I recommend you do is to graph it. See visually what you're looking at. If you don't want to use MATLAB, that's fine. You can use Desmos or whatever. I just want you to visualize what you're doing. And in this case, we have the function and the derivative. Okay. And then for regular falsi, you can see the examples. You can see the examples in your book. So check example 3.1, and they have their own script that it can help you get started. The regular falsi question doesn't say that the answer has to be stored as xn. Good. Okay, thanks for that. Yeah. Thank you for that. Let's make sure we. Okay, I'm gonna double check that because I think some people had issues with that. So I'm gonna double check that. Thanks for that. So yeah, so what I mean by doing it like manually is you can have some initial guess, and then you can define the anonymous function. Something like this. And then sign effect, right? And then you can start to build your own for loop. For I equals 1 to 10. And then some algorithm here, and then end it. This is optional. Optional. Okay. Okay. And then I'll tell you what to store it as. I think you need to store it as XNS or something. XN. XN. I'll double check. Let me double check. Final answer. But if you don't want to do the for loop, you can just do like, right, you proceed with the algorithm. So let's check the algorithm for this guy, right? So we have some initial guess. So we can define some A, define left bound, define right bound. And then you want to plug in these equations. So you define your f of x, right? And then calculate f at a. You can have your fa stored as that. Define initial guess for function at a. Something like that, right? So this isn't complete yet. So if you run this, it's not going to work. I want you to try that out. And then if you get stuck, then let me know. All right. Otherwise, if you have any questions, again, let me know. So this is technically due at the end of class today at 11 a.m. If you need more time, you have no later than tonight at 11:45 p.m. And stop recording.